Well, guess what? We are ready to get started. So I finally got the computer and the camera to talk to each other, and now we're actually live streaming. So hello everybody on Twitter, YouTube, and Facebook. So thanks for coming out tonight. We are here because Nanome is a business here in San Diego, which is a VR-based nano engineering and molecular modeling company. And they are in this building, so thank you to Nanome for letting us use their conference room space at this facility here in San Diego. Yes, thank you to them. And then thank you to Edge, who helps sponsor and cover the food and drinks that we're enjoying this evening. So thank you to Edge. Get your Edge wallet if you don't already have one. So thank you, Edge. And then my name is Chris Groshong. I run Coinstructive, and we're a consulting company, and we do continuing education for professionals in the industries of law, banking compliance, and law enforcement. So today, actually this last week, I went to a meetup on Monday by the Blockchain and Brews guys. Those guys are awesome. They're here in San Diego, Rocky and Barry. And we're trying to bring the community together more. So we're really working to try to build a more harmonious and a group that brings together everything that we're doing, is instead of fractionalizing or fracturing everything and having people go in a bunch of different directions. So we're hoping we can work with them in the future. Also, I'm going to be running the Government Blockchain Association San Diego chapter, because I've been doing a lot of policy and regulatory work on my own, especially now in California, that it's really coming to a head that we're going to be doing the Virtual Currencies Business Act, and that's going to affect a lot of California-based companies. And a lot of the people who are making laws don't necessarily know exactly what they're talking about. So I think the next 12 to 18 months are going to be very critical, and so I'm spending a lot of time doing that. And so I felt it was important to start bringing in the elected officials and other civil servants so that we can explain to them, so that they can understand, because as soon as laws start happening and then their constituents start complaining, they're going to have to learn, right? So maybe get out ahead of it a little bit and learn as we go, so you're not cramming at the end. So that's what I'm going to be working on in the early part of 2020. At the end of the month, or in the middle of the month of December, we're looking at, I think, December 19th. I know it's close to the holidays again, but we're going to try to have a holiday party here in San Diego. So if you're around, we found some money in a copay wallet. So, and by money I mean Bitcoin, because Bitcoin's not really money. but you know, it depends on how you look at it. Apparently, it's also a good store of value. So somebody had found their wallet because we were down to 1 out of 5 that had their keys, and we needed 2 out of 5 to send the money. So luckily, we got it taken care of. We moved it over. But this is what happens when you work with an organization that's loosely based, right? Things, you know, when you were putting 20 bucks or 40 bucks a month in, and then you turn around and you go, oh, there's a couple grand in there now. Maybe we should have a party. So holiday party, December 19th. And that's pretty much all of the housekeeping I have. At the end of the event, if anybody has any announcements they want to make about other groups that they are involved in or things that they're working on, feel free. We'll let everybody come up and talk at the end. They can have up to 2 minutes to kind of give their spiel about what they're working on, who they need help from, or what their interests are in the space. So today's meetup is going to be something that I'm interested in very much in learning about. And I had the pleasure of meeting the CEO of Casper Labs in LA during LA Blockchain Week, and found out that she lives in San Diego. So I was able to wrangle her to come in, and she's been on the road for quite a while and home for the holidays. So we decided to have her come in and teach us and explain to us and see how we can take advantage of utilizing the Casper Labs protocol. And so without any further ado, I'd like to introduce CEO Medha Parlikar.
Thank you so much for that warm welcome. Love San Diego. I'm super happy to be presenting locally. Our fellow cryptocurrency enthusiasts here in San Diego. And I'm all for bringing us all together, and talking to government officials. So let's connect afterwards and let's figure out what the next steps are, because I'd like to be there right there with you. You know, Casper Labs has offices in California. So we're definitely have an incentive to work with regulators and work with lawmakers to help educate cryptocurrency and tell them it's not all frightening and scary. So that would be a great thing. So yeah, today we're going to talk about the Casper Labs company, the blockchain that we're building, and then also more broadly, the family of protocols known as CBC Casper. So I'll talk a little bit about myself, and then a little bit about the company, and then we'll dive right into, why the company's here, and then we'll dive into the protocols. So again, my name is Medha Parlikar, and I run the engineering team at Casper Labs. Casper Labs was founded on Halloween of 2018. We like to say it's exactly 10 years after the release of the Bitcoin paper. Casper Labs was founded, and we were founded because we believe that the CBC Casper protocol has the potential to scale out blockchain and address a lot of scaling concerns in the space today. We are a team of about 35 individuals. About 27 of those folks are in the engineering team. 4 of the folks are based in San Diego, so we have folks here in the US, we have folks overseas in Eastern Europe, Central Europe, and we have a couple folks in Asia as well. So I'll just dive right in with that. So of course we know about the first generation blockchains. It solved some fundamental issues. Bitcoin gave us the notion of crypto economics by stitching together several technologies that are well known, hashing, Merkle roots, and the distributed ledger technology. But when you put it all together and add crypto economics on it, you have this wonderful thing called Bitcoin. And then Ethereum was a incremental improvement on that by adding distributed computation or smart contracting to this blockchain concept, right? But Ethereum is serialized. It's a serialized proof of work system, and it's limited at 15 transactions per second. And interesting story on the history of CBC Casper, because we're talking about Casper today. Vitalik knew that almost immediately after releasing Ethereum that he was going to be facing scaling challenges. And so he reached out to a mathematician that he knew in his circle, Vlad Zamfir, to kick off research for a scaling solution for Ethereum. And so Vlad embarked upon building and creating CBC Casper around 2014, 2015, very shortly after Ethereum was launched. So this has been a project that has been in the works. The research has been going on for many, many years. And so, scale has held blockchain back, right? You see a lot of dApps being built on Ethereum. There's a lot of desire to adopt a main decentralized chain, but you've also seen a lot of these private chains pop up. You've also seen this generation of blockchains come into the space that have used things like optimistic consensus or centralizing the validator set by limiting the validator set because they want to limit the consensus overhead, right? Because building a decentralized protocol that can scale out is really a problem. And the scale issue is a little insidious, right? Because when you think about the economics of scale, you can't take advantage of economies of scale with blockchain right now, the way it's designed. Amazon's able to reduce its pricing, but you don't see that when you start talking about blockchain because you can't add more distributed compute because ultimately the entire system has to come to consensus on the state of the machine. And so what you need is a more innovative way to think about this virtual machine state and consensus protocols more broadly. And scale also matters because when you think about economies of scale, you start thinking about cost, right? And so we've observed with Ethereum, especially during the alt craze of 2017, that the price of Ethereum went through the roof, but more importantly, the gas transaction fee went through the roof, right? And you had this surge pricing because you've got this market for gas, right? And it's very, very logical. The gas model makes a lot of sense, but when you can't scale out the blockchain with the economies of scale, you run into this surge problem, right? And businesses will not take that kind of risk on, right? It's not even my utilization that's driving the price up, it's the guy next door, right? It could be his utilization that's affecting my costs, and that's not tenable for business. Oh no. So this is why we've built Casper Labs. We're building something what we call the blockchain for builders, and we want to scale opportunity for everyone. And we believe that this innovative consensus protocol that is going to be secured through economics will enable the blockchain to scale without sacrificing security. So real quickly about the company, we want to remove these barriers that prevent adoption, right? So we want to provide a fully decentralized system that will scale, that will provide the speed and security that businesses need. Additionally, hidden underneath that is going to be price stability, right? So there will be, because you can scale the protocol out, you can offer stable prices for businesses. We want to have familiar tools and open architectures that make it easy for any developer to become a blockchain developer. Our execution engine is built on WebAssembly, and currently smart contracting is supported in Rust, but we're going to be adding support for assembly script / TypeScript. And as more compilers are built that compile to WebAssembly, we will naturally be able to include contracting interfaces into our system for those other languages, right? So we've set ourselves up to basically provide open access. We can do C, C++ if we want. We've already done Rust, and we're going to do assembly. Want to be open to the world, right? So we want to provide a platform that enables everybody to participate as a validating node, everybody to participate as a developer, and make it really easy to even be a dApp developer as well. Future-proof, this is really important. So the CBC Casper protocol, it's a really hard protocol to get right because it's very abstract, right? Most of the consensus protocols that you see in the space come to consensus on the canonical order of transactions. CBC Casper does not do that. And more importantly, the Casper Labs blockchain has this concept of commutativity, right? So because the blockchain and the execution engine are all concurrent, there isn't a hard ordering of transactions unless the transactions conflict. Furthermore, with the consensus protocol being abstract, it enables us to shard it in the future. So because the protocol doesn't care about the order of transactions, you can actually shard what's in a block. And this is very purposeful from Vlad's perspective, that the consensus protocol has to not care about the order of transactions, so then you can start splitting up and sharding up what goes into the blocks themselves. We can dig into that a little bit more. The sharding research is still very much research, so we haven't actually landed on how the actual sharding implementation is going to work just yet. So let's start digging into CBC Casper. So as I indicated, it was proposed by Vlad Zamfir of the Ethereum Foundation to address scalability and energy. The 2017 paper I think it's 2017 or 2018, November 2017 or November 2018 paper for CBC Casper is a simplistic family of protocols, right? And we'll talk about the simple version of CBC Casper, and then we'll talk about the full protocol, right? So CBC Casper specifies this as protocol that is provably safe. It does not specify a liveness proof. And so if we talk about safety and liveness with consensus protocols, safety means that transactions are not reversed. Liveness means the protocol always comes to a decision. So the purpose of a consensus protocol is to come to consensus. If you have a consensus failure, your protocol is dead, which means it's not live. So that's what liveness means. So diving in, right? CBC Casper punishes bad behavior. So if a fault can be detected on the network, you're slashed for that fault. And I think this is really important, right? You have to have, if you're going to have a proof of stake protocol, you have to have bonds and you have to be able to slash those bonds, right? Because you have to have an economic incentive for good acting. So it will punish for equivocation, which is an inconsistent decision. What that means is basically I was building on this block and now I've decided I'm going to go build on that block, right? That's called an equivocation. So you're basically reversing a decision you made before. Invalidity means I'm selecting either a block that should not be a parent of a block. So maybe this block is the heaviest block, but I'm choosing that block over there. That's an invalid block, right? So I'm making invalid or inconsistent and incorrect decisions. Reversion is obviously reversing a transaction that I previously approved. All of those things are what we call slashable events and are detectable in the network. Abstract and future proof, I talked about that. Increases decentralization, so you can have minimum and maximum staking amounts. So depending on what the level of participation is and how many validators you want to scale out, you can set your staking threshold wherever you wish. So validators need to only procure their bond, send a bonding request, and then they're joining the network, right? So you don't have to go through any kind of voting mechanism. There's limited ability or no ability to form cabals because it's an open and permissionless network. It increases energy efficiency, right? So there's no hashing required. All the compute goes towards processing consensus or processing transactions. And it increases security because an attack can't revert a finalized block. So if you think about attacks in proof of work you can start mining an alternate chain. But nobody's going to walk in through your front door and take your rig. Right? In proof of stake, if you try to attack the network, your bond will be slashed, which is your primary capital, right? Like that's a big chunk of capital that you're putting up. More than the computation that you're putting forth on the network, your stake, your bond is really a big financial hit. So there's a real adverse consequence. There's a real consequence to attacking a proof of stake network. So this is an example of a basic Casper blockchain. So you'll see here we've got the Genesis block here. You have these arrows here. These are called justification messages. What you're being shown here are what we call parent justifications. They're similar to saying, well, I've seen that block and I'm building my block on top of that block. Parent justifications are a feature of Casper specifically. There are also other justification messages which mean that even though I'm not building on that block, I've seen that validator's block and I've processed that block and I think that block is valid as well. So there are blocks that I'm building upon as my immediate parent, and then there are blocks that I've observed in the network that I also consider valid. When a validator, which is the term for a miner, when a validator builds a block on top of another block or sends a justification message pertaining to that block, the block's weight gets heavier. And what is weight? Weight is basically, it's the percentage. So if you talk about this notion of weight on a block, it's the percentage of stake that has voted for that block by building on that block or incorporating that block into its global state. So for example, if I'm running a node and I've seen this block, blocks are being gossiped on the network and some of those blocks make it to my node, I see those blocks, I observe those blocks, I pick a parent, and then I build a block on top of that parent block. I build justifications. There's specific justification messages that are part of the block that indicates that I've seen those blocks and I've sent messages about those blocks. And this is the way, oh no, validators vote for blocks in CBC Casper. Experiencing technical difficulties. I think I need some help. Both of them crossed. I swear I didn't touch anything. Really? Okay, I'll carry on. So validators, these are bonded actors that produce protocol messages, and each has a weight based on how much they bond. Justifications are the causal relationships between the protocol messages. When we talk about Casper and the ghost rule, it's the greediest, heaviest observed subtree. So what that means is LMD ghost means my latest messages, which is the most recent messages my validator sent, have to always vote for the heaviest block on the network, right? So it's not, if you're following the protocol as a good actor and you're sending valid messages, you're always voting for the heaviest block. And so you can kind of see that there's a little bit of an equilibrium that starts forming around the amount of blocks that I propose as a validator and the stake that I have, right? So there's an incentive that if I want to propose more blocks as a validator, I want to have a higher stake, because by virtue of that, more of the blocks that I produce have a higher weight, more of them will get finalized. If that makes sense in the protocol. Yes. Don't touch it now. Don't move. Stay there. No, I'm kidding. So here, one of the interesting properties of CBC Casper is it has provable safety. And so when we talk about provable safety, what that means is if you think about the fact that the validators, when they send a bonding request, there's a special contract that lives in Casper called the proof of stake contract, at least in what we're building. There's a proof of stake contract, and in that proof of stake contract, you have a list of all the validator identities and their bond amounts. So from that, so if I send a bonding request, my bonding request goes to the proof of stake contract, and once that block that contains that transaction gets finalized, all the validators will see my validator ID and my stake amount. And once that block makes it back to my node will see itself as being bonded. So that's the bonding process, right? But understand something, that in any past cone before that block, I have no stake in the network, right? So what that means is if I want to join the network as a malicious actor, I'm not setting parameters, right? Like we can measure based on the current token price and the amount of bond on the network. We can actually measure the amount of financial security behind any given block, right? So for example, if you have 100% slash and you've got, $1 million of stake on a given bond, on a given block, then you have $500,000 of economic security for that block, right? Because the validators would have to collectively equivocate $500,000 in order to steal transactions from that block. And so the thinking is that over time, as the value of the network would increase, so would naturally the economic security of the network. So here you can see the orange validator is attempting to attack the network by mining their own chain. A few interesting things happen. One, the blocks, those orange blocks being proposed, will not have that much safety, right? Because none of the other validators have voted or seen those blocks, right? So he's attempting to mine his own chain, and similarly as you would in proof of work. But the problem becomes is you need the balance of the stake in the network in order to get those transactions to be safe. Those transactions are not safe right now because these other validators haven't haven't built on those blocks, haven't pointed any justifications to those blocks. So And in so doing this block A9F2 0B9BB2, the blue one in the middle, its safety actually goes up because this validator, the orange validator, is actually building on top of that block. So he's actually adding more weight to that block by building on top of it. That makes sense. This basic Casper blockchain also resembles a lot of what is being done in Casper FFG for Ethereum. So to talk a little bit, I'm just going to gloss over what Ethereum is doing. Ethereum in Ethereum 2.0 is adding the safety properties of Casper that I'm describing here to the proof of work chain, right? So 2% of the blocks in Ethereum 2.0 will be finalized using CBC Casper. Validators will put 31 ETH up to bond to this chain, and they will vote for blocks in a similar manner that is being described here. And what will happen is you will have these checkpoints where a fork choice tip of the proof of work chain will become finalized. And it's this property that will basically provide Ethereum a way to actually have these notion of checkpoints, right? And some interesting things happen with checkpointing. You could choose if you want to prune away state, right? So once a transaction is completely finalized, it's irreversible. You don't necessarily need to keep the actual blockchain ledger, right, in every single machine state, right? You could have archival nodes that would hold arguably the entire blockchain history, but then you could have light clients that would only keep n number of checkpoints in history. So there's some interesting things that can happen once you have checkpointing implemented, and I suspect this is part of the longer scale plans for Ethereum 2.0 as well. So I'm going to talk a little bit about the Casper Labs Highway protocol. This protocol will balance both liveness and performance. As I indicated, the CBC Casper protocol that went out in the paper is only a safety strategy. It's not a provably live mechanism. Provable liveness basically means that so you can attack CBC Casper by selectively censoring protocol messages, right? And so even a low stake weighted validator could arguably say, well, I'm going to see this validator's messages and I'm going to see that validator's message, and they can bounce back and forth which chain they want to put or which subtree they want to put their weight against. And in so doing, they could literally cause the chain to flip-flop, right? And this is a known provable issue with just the basic CBC Casper safety protocol, a safety proof. So we came up with a liveness proof, and this was thanks to Professor Daniel Kane at UCSD in collaboration with Vlad and Andreas Fackler on our research team. You can find the paper online. So, a little bit of hand waving here because this Nakamoto consensus is actually also properties of CBC Casper, right? We have this notion of variable safety, which is very similar to confirmations in proof of work. The variable safety means I can choose how much safety I want in a block, whether I want a small portion of the network to build its stake upon it or a large portion. So that is a feature of CBC Casper. Basically, clients can decide when they feel a transaction is finalized. We have very low message overhead. Right now, we have O of n message overhead in our current protocol. We want to get that down to O of 1. And what that basically means is if you look back here at justification messages, you can imagine if the network gets very large, these are parent-child messages, but if this validator saw his block, and this validator saw this block, this block, you start seeing that every validator has to send messages to every other validator, and so the network can get very noisy, right? And there's other fork choice type protocols out there. Tendermint is a good one, the one that Hedera Hashgraph is using. These protocols limit the validator set because you get to have a lot of network overhead, right? Because it gets very noisy. With 1,000 validators, you have now 1,000 times, factorial, each of them sending messages to each other. And so we have a mechanism by which our goal is to basically get to a point where we can have a liveness proof where you're only voting with blocks that contain transactions. And that gets you to Nakamoto consensus overhead. We have validator set rotation. We have this notion of validators instead of miners, and we have staking instead of electricity investment. And then we have the 51% attack resistance for equivocation. But then we also have is transaction finalization, and we don't require hashing difficulty increases, right, to increase the security of the network. So the highway liveness strategy. So I'm going to talk a little bit about this. If it gets a little complicated, I apologize, but it's a complicated protocol. So it's what we call a partially synchronous protocol. So what is a partially synchronous protocol? If you think of proof of work is a fully synchronous protocol, right? A fully synchronous protocol means there's only one block on the network at any point in time. A partially synchronous protocol means there are multiple blocks on the network at any point in time, and validators are producing and processing blocks in a partially synchronous manner. And we have this notion of lanes, right? So the validators will say which lane, there's a cryptographic method that they will say, this is the lane that I think I can be in. I think I can be in this lane, and by virtue of that, I will take the role of leader at some interval, okay? So kind of from a high level perspective, 3 concepts in the liveness strategy. One, we have this notion of leaders. So at some point, every single node in the network has to propose a block and demonstrate that they're live. They also have to propose votes for every single round. So we've got leaders, rounds, and then we have this notion of lanes. Okay, so the lanes provide the partial synchrony. The leaders and the rounds provide the liveness strategy. So in every round, everybody has to show up at least some percentage of the time, depending on which lane they appear in, right? So the slower validators that may have less processing power and less bandwidth may not show up for every round, but they may show up for certain rounds, right? So you can imagine that there will be this notion of this heartbeat, right? So you'll have everybody syncs up here in this round, then you may have 2 or 3 rounds with the fast validators, and the slow everybody joins up in this round, right? And so on and so forth. So there's this point where the entire network will synchronize when the slowest validators catch up. Each round will last, so there's this notion of ticks, and each tick you assigned a leader. So arguably there's a new leader every millisecond, and each round will last 2 to the n ticks, depending on what the rate of n really talks a lot about these different lanes, right? So depending how slow the slowest lane is, that's when you'll have the rounds swapping out. Okay, so what will happen is there's this round exponent n, which talks about how quickly are the blocks being agreed upon, right? We have this notion of summits. So basically it's like you have layers of agreement to finalize a block. So you have one layer of agreement, then a second layer of agreement, and then finally a final layer of agreement is where those transactions become finalized, the round completes, and you do another round. And so this round duration is flexible depending on the amount of time it takes for the right number of validators to show up from a liveness strategy, right? Remember, the liveness strategy is to make sure that everybody is sending messages correctly. So what you want is you don't want to have a fixed round duration. You want the rounds to actually be flexible depending on network conditions and depending on how the validator set changes, right? Because every week we'll have validator set rotation, so as some validators may leave, new validators will join, and so this round exponent, which is the round duration, needs to actually also be fluid. The goal of the protocol is to actually enable us to optimize for network overhead and time to finalization, right? So if you think about the more messages you have in the network, arguably, you could potentially have more overhead, which would increase the consensus overhead to actually determine if a block is finalized, right? Because you have a lot of protocol messages to sort through and compute to understand, okay, what actually is the safety of this block, how many validators have sent justification messages, and what are the aggregate weights for each validator. So that computation could get very expensive if you can't adjust for this network overhead. So this is what the DAG looks like. So I'm going to talk a little bit about, so if you see this choke point here, that's the leader, and you see these lines of agreement, you can think of these lines of agreement as summits, right? And so what you're seeing here, I don't have a pointer, but maybe I can do that. Oh yeah, I can do it this way. So these are primary parent justifications. These are what we call secondary parents. So in these, now this is a feature not of Casper, but it's a feature of our specific implementation of Casper. We have in our blockchain this notion of block commutativity. And if you guys want to know about the deeper architecture, I can share it with you. But in essence, if Alice sends Bob money and Charlie sends David money, those transactions have nothing to do with each other. Those blocks can essentially be merged, right? So if I'm getting multiple blocks coming in from the network, provided those transactions don't conflict, I don't need to impose a total order on those transactions. I can just merge them together and actually build a block with all of those blocks as parents, right? I don't have to pick a single parent. This is really important for dApp developers because orphan transactions are the worst thing ever, right? So we don't have to orphan transactions in Casper Labs. We can actually pull in all the transactions. The only time you see an orphan block is an example that we actually had in our testing session today, is a validator's state is not completely caught up. They're like 200 blocks in the past, and they propose a block. That block's going to get orphaned because it's in the past cone. None of the validators have seen it. There's no way for them to send justification messages to it, so those transactions just hit the floor, right? They become orphaned. But if your state is up to date and you propose a valid block, your block will be included in the canonical history because we have this, we call it snowball. We kind of scoop everything up and try to finalize as many transactions as we can. And so you'll see these layers of agreement, and then the leader proposes a block and it synchronizes and those blocks become finalized. And so here's an example. You can actually see here this notion of parent justifications, secondary parents, and then just justifications. So the dotted lines you're observing there are the justification messages from the other validators that's saying, I've seen this block, I haven't built on it, but I saw the block. And I'm giving you a justification message that I've observed this block on the network and I consider it to be valid. That's a dotted line. The heavy line is a parent block, right? So those are the parents of this block. So you'll see here this block has 3 parents and 4 children. And multiple justifications for seeing that block. So that's how you can say that in all probability this block is going to be finalized because it has a lot of weight on it. And this is actually coming from our Explorer that's live. So that's it on the protocol. We can go into more depth later on if we want. I'm going to talk a little bit about smart contracting platform and the system itself. So on our platform, transactions are a deployment of WASM bytecode to the blockchain or the calling or invocation of an existing contract that's already been stored on the blockchain. Yes?
Sorry, I should have asked it before you went forward. But, okay, so it's proof of stake. You have to, put up or shut up, so to speak, right?
Mm-hmm.
What stops people from jumping on blocks that they're going to profit from? They're going to profit more from it. Leaving the orphan that's hanging out there for somebody else to do, or just, shoving them aside, or, when you're doing.
So that's a liveness failure. When you're censoring a block, what you're talking about is I'm not going to process this block because it's extra work that I don't want to go into, right? But if I don't process that block, now what's happened is my global state of my internal virtual machine is not up to date. So I've missed a bunch of transactions that everybody else has. Now, if I attempt to propose a block and my global state isn't updated, my blocks could potentially be invalid and I'll get slashed for that. Oh, thank you. So there's that incentive, right, to do that. The incentive to be the leader is that the leader will get a large number of the transaction fees for that block, right, because they're actually doing the heavy work of doing the consensus work of processing all the votes, potentially processing all the transactions and synchronizing the network, so they would get a big chunk of the fees, but not all the fees, right, because every validator participating in the network is providing value by adding security to the network, right? But since everybody gets to be a leader, everybody gets their turn to have transactions. So you kind of couple that with deploy gossiping as well. So when you send deployments, you gossip those deployments to the network so that everybody has transactions to process.
So
Did I answer your question?
Yes, but with the proof of stake, how much are you talking about? I mean, when you have people come on board, how much money are they willing to put forth and lose?
Yep. Yep. So it depends on the size of the network that we want to go out with. So ideally later on, we see in 3 to 5 years when the network is fully scaled out, you could have potentially side chains or change where the amount is as low as $1,000, right? And it's not a lot. But you do receive rewards, right? So the idea is that yes, you're putting up a bond, but if you're an honest actor, it can be very profitable for you, right? And so eventually, the desire is that people can participate in this network and use it as a nice way to make some income.
Now, when you're talking about bond, are you talking about a legal, an actual bond? Like, I refer to it as the real world, but it's not really. But
It has the same principle, but it's not a legal bond. But it is basically you are acquiring tokens for a certain amount of currency, arguably fiat currency, right? Or Bitcoin or ETH, but you're acquiring tokens for some amount of value, and then you're taking those tokens and you send it to the proof of stake contract in a bonding request. And the proof of stake contract holds that. And if there's cryptographic evidence that you've done something to harm the safety or liveness of the network, those tokens will be slashed, they'll be burned.
I see. So do you actually do a background check on the people that,
No, there is no check. There's no permission required to join the network at all. Very much like Bitcoin and Ethereum, right? Like you don't have to ask anybody. You just download the software, provision the hardware, sync up your state, and off you go. So talk a little bit about transactions. So parts of a transaction. So we have this notion of payment and session code. A payment amount, a private key, and some parameters. So I think payment amount, private key, and parameters are fairly obvious for anybody that's done any kind of deployments or transactions with the Bitcoin blockchain or the Ethereum blockchain. What's unique with the Casper Labs blockchain is we have this notion of payment code. So we offer a Turing complete payment code solution that enables businesses to basically create any kind of interesting transaction payment paradigm they wish. So if you want to do debit cards, specials, referrals, you want to pay for the first 10 transactions for your customers, whatever you want to do, you can create custom payment code and build that into your application, into your decentralized application. So we think this is a very interesting and powerful feature because right now in Ethereum, sender pays, right? So if I want to do something on CryptoKitties, I have to pay. It's not CryptoKitties' problem, but we think that real businesses will want to obfuscate that for their customers and provide a subscription model or something. I pay $20 a month for some service, and then I don't have to worry about obtaining the token or any of that stuff, right? That's the way traditional businesses run, and I feature that they would want to do the same thing with the blockchain. We have this notion of unforgeable references, which is a flexible permission model. So the great way to think about unforgeable references is, the Casper Labs blockchain is a public blockchain. It's a public decentralized blockchain. We do not have private data on our blockchain. But what we can do is we can offer to protect that data. Similarly, with cars parked in a public street, cars in a parking lot, you can see the cars, you can observe information about the cars, but you can't drive the cars. You can't do, arguably, anything to the cars, without having the appropriate access. And unforgeable references work the exact same way. So you can have contracts and contract data that only contracts that you specify can modify, right? So your contracts will be stored and your unforgeable references will be stored in the context of your account. And only somebody that has that unforgeable reference will have any means by which to interact with your data or interact with your on-chain contracts. And this enables developers to break down their application into like public and private methods. So if you think about this concept of private data and private methods in traditional computer programming paradigm, this allows for the exact same thing, right? You can have these private methods that are only accessible by your contract and not by anything else. even though they're on a public blockchain. One thing to note, once you share the unforgeable reference, you cannot unshare it, right? So once it's out there, it's out there. The only way to revoke those permissions is to, remove, delete the unforgeable reference and regenerate a new one. So weighted keys. We have this very interesting thing called weighted keys, which is a built-in multi-signature feature. We believe this will provide a lot of really interesting things that dApp developers can do. So they work with deployments, so you can specify in your contract a threshold. And it's an arbitrary number, whatever you wish to specify. Let's say, for the example, for this case, we've got this required weight of 50, right? So in order to run this deployment, I need to have a key weight of 50. That can be made up with 5 individuals with a key weight of 10 or 50 individuals with a key weight of 1, right? But the requirement is that I have to have a key weight, an aggregate of 50, before that transaction can go to the blockchain. And this is really, really easy to implement. It's very scalable, right? It's not like you have to create this complicated multi-signature contract, right? It's actually baked in. All you have to do is set the threshold in your contract, and then you can assign keys and weights to these keys and then just send the keys out, right? You can use this things for, like, if you imagine signing things like besides multi-sig of a check, but you could even think of, like, at work, if you wanted somebody to authorize a time off, right? Maybe the HR manager has a certain level of authorization with the vice president, but then the CTO may have full override authorization because he's got a weighted key of 50. But the other individuals may only have weighted keys of 25. So they both have to sign to approve it. And you would know that automatically by looking at the signatures. You would know who signed the deploy, right? So, but this makes it very easy to implement that versus a long, complicated contract for developers to build. This will also facilitate account recovery. We haven't implemented account recovery right now, but you can imagine you could have a master key that has all the weight and then child keys underneath it, and an action from the master key would basically recover all the funds from all your child accounts and move the funds to your master, right? So this feature grew out of the desire to have real end user account recovery, because that's like a real problem when you start dealing with a secure enclave and lost phones and lost keys and that kind, right? So being able to provide a mechanism for users to recover their accounts for blockchain is really important. So we also provide, we believe blockchain is part of a system architecture, right? So I don't see blockchain as being the entire architecture unto itself. I see real businesses building an architecture that will involve blockchain over here. There'll be mobile, there'll be web, there'll be business, BI, analytics, there'll be identity and user management, and blockchain is going to be a piece of that. And you will need to interact with the blockchain component just like you would interact with your off-chain components, right? And using Rust and assembly script gives us a very interesting benefit compared to Solidity, because I can build a Rust application and point it to a SQL database. And I can code that all up, I can run it locally, and then I can create a version of that application using blockchain APIs, right? So I can actually do A/B testing, where I'm testing the performance and behavior of my system against a central database versus a blockchain system, right? And so if you think about even going live, right, in a real production scenario, having this kind of an architecture makes it really, really easy from a business perspective, right, to know that the system is behaving correctly and really to separate what's an issue with my actual application versus what is an issue with how I'm interacting with the blockchain. We offer GraphQL to let people interrogate the global state and understand what's going on there in terms of their application insights, how their application is performing, state of local variables, et cetera, et cetera. And we're going to provide the capability to versions on-chain contracts, and as well as registering them in a name registry, but you can actually upgrade your contracts as well, right? So being able to upgrade contracts is hugely important. And also we plan on providing dApp developers a way to pick a protocol version. So in the event of a protocol fork, dApp developers can actually build a kill switch in to say, well, I'm going with this version of the fork, right? I'm going to go this way or that way in the fork. If there's happens to be a blockchain fork, they have control over which version of their dApp is working. And then the desire is that the architecture is very simple, right? The reason we have weighted keys, flexible payment code, UREFs is to create a very simple and maintainable architecture, which will make going live a lot faster, right? And less code to maintain is less risk for bugs and quicker time to market. And that's it. Let's start building. Thank you so much for your attention. If you have any questions, I'm happy to answer. Thank you very much. Yes.
Okay, so how clients work currently is if you're trying to download all the information of, say, currently Ethereum with the Geth client, you're not just getting the data, you're also doing all the transactions and computing it locally, right?
Correct.
Okay, so when those dotted lines, when you were showing the different shards communicating with each
The
other,
justifications, yep. The different, yep.
that's just grabbing the state, not doing the computing of the other shard?
It's not shards. Those were just validators we were describing, not shards at this, in this presentation. I was not describing shards. Yeah, it's okay. I was only describing the validators themselves. So here, if I can go back, or the blocks actually, validators in the blocks. So I can walk back. It's quite the mouthful. Oh, this is a good screen here. So the validators in this picture here, the pink is validator 1, the red is validator 2, the green is validator 3, 4. There's 5 validators in this network, okay? And each of those dots is a block that the validators produced, okay? And so what you're seeing is the justification messages are basically the data that is stored within the block. I can actually show you that here. Hold on, and show here. So, can you guys see that? Let's do this. Oh, it's going to ask me for the depth. Maybe one. So this is actually the data that is stored within the block. So what you'll see here, this is showing me the most recent block, block 797. And what you're seeing here is this is the hash of the block. This is the hash of the parent block. And here are all the justification messages. So the parent hash you'll see is that thick line that you saw in the image. The justifications are the dotted lines that you're seeing. So when they download a block, when they're syncing up, this is the block this is the information that they're going to process to help build what we call the DAG, right? So we have a representation of the DAG in a SQL database that also lives on the client. And this is the relationships that's built. This becomes important later on because you want to identify which block is finalized, or sometimes you want to figure out what the latest common ancestor is in the event you have to revert, or there's an equivocation, or something like that happens. You need to be able to go back and figure out what is the latest common ancestor for all these blocks. And that's what that choke point is that becomes the latest common ancestor for all the blocks before it, right? And like a finalization point, for lack of a better term. And then here you'll see this is the pre-state hash, the post-state hash, and these are all the bond amounts. So we talked about the bond amounts going into the proof of stake contract. This is the information in the block that talks about these are the validators that were involved in processing this, in the network at the time that this block was processed. It's the state of the proof of stake contract. Did I answer your question?
I guess my question had more to do with, so those dots being validators, they won't communicate with other parts of the network until they all come together.
No, they're constantly communicating with other parts of the network. The block propagation is happening all the time, right? The justification messages that you're seeing here are basically that I've seen this block. I got the block, I've seen the block, I acknowledge the block. It's just not the parent block that I'm immediately building on top of, but it is part of my state, it's part of my DAG. But it's part of my DAG in a slightly different way. And so one of the things you can see immediately with Casper is that we have this notion of this past cone, right? So all of these blocks arguably have transactions in them, right? They could all have transactions in them. And so what you see is the network eventually all those blocks get propagated, and provided that none of those transactions conflict with a double spend, right? They all eventually make it into the global state. And so Casper has this interesting notion of becoming eventually consistent, right? Because it's partially synchronous. So this enables us to scale out throughput significantly more, right? You can already see that we don't have orphaning, right? Because you see this multi-parent implementation. You don't have to just choose one parent, right? You can select many parents, and you can also choose to acknowledge blocks through justification messages, even though you're not building directly on top of them. Yeah?
I noticed in the example block data structure you had that the parent hashes only contained one hash. Is that just a peculiarity of that particular block that you
Yeah. It's,
Can you repeat the question too?
yeah, I'll repeat the question. So the question is in this data structure that I showed here, he is observing there's just one parent hash in this block. And yes, the reason that there's only one parent hash is just because this particular block was only built on a single parent, right? This usually will happen because there's not that much traffic on the network, right? So you don't have, the node isn't seeing multiple blocks coming through at a time, and then when it gets to build a block, it's got multiple that it builds on top of. So it's more of a function of traffic on the network, right? There's very low traffic on the network right now, so it's just a single parent. I think he has a question. Yeah, go ahead.
You said earlier that there's no block increased difficulty in a proof of work system. How do you bootstrap security in a proof of stake system?
That's a great question.
It's the underlying token value is a big part of it, but how do you get that initial like chicken and the egg problem?
Yep. Yeah. So
people to participate if there isn't a huge amount.
that's right. That's right. So proof of stake, all proof of stake networks have this problem. Every single one of them. So CBC Casper and Casper Labs is no different than any other proof of stake network. You have a bootstrapping problem. And so the way this has been solved, and we are in Switzerland as a jurisdiction. So Switzerland has actually issued guidance on this very topic from a regulatory and compliance perspective. There is this notion of Genesis validators and what is called a private validator sale. And so the private validator sale enables companies to acquire the necessary stake to secure the Genesis block. So companies, when they feel that their Genesis is 30, 60, 90 days out, or they're in testnet, or some time at which they deem that they're ready to start talking to prospective validators, they will engage in a preliminary validator sale. They'll have to figure out a prospective valuation for the network, and then they sell some portion of the tokens to those validators to acquire the initial stake. It is our plan to do that, yeah. There really is no other way to secure a proof of stake network.
Anybody else other than Switzerland have regulation around that kind of?
There's a few countries that are really, Estonia has some regulation around that too. They're trying to be very crypto friendly. Some of the countries in the Bahamas and Grand Cayman are actually working on it. I know Wyoming is blazing a trail, but we all know about how the SEC is doing things here in the United States. So any kind of validator sales have to exclude any and all US residents. Sometimes if you have savvy accredited investors, they could potentially participate in a validator sale. But a lot of companies right now with most recent guidance from the SEC are even avoiding that. So there's a few countries that are favorable for crypto where you can basically run your operations out of that country. You had a question?
Yeah, about the parent hashes. So the specific model that I want to parent hash, and just correct me if I'm wrong, so I understand it. If you specify a parent hash and in creation of block, that means that you are kind of giving validity to that previous block. Like some of what you staked as a validator is getting credit for that previous block. If you specify two, is it just giving like half of the one, half of the other, or do you get to specify what percentage of your stake goes to one half versus another?
Right, so the question was, in this particular block, we're seeing a single parent hash, and based upon that, it's safe to say that the stake weight was being added to the block upon which I'm being built. If there's multiple parents, does my stake get split? And the answer is no. Your stake gets put on both of those blocks, right? Because in the event either block gets reverted, you'll be slashed for that, right? So because you're building on top of both blocks, you're in essence voting for both blocks with your full stake, right? So the stake doesn't really get sharded or split per block. The idea is that if any single block is equivocated, if you equivocate on any given block, your stake will be slashed, right? Right now we're going with 100% slash because that increases the security of the network. But you'll lose all of your stake for any given block that you have equivocated on.
I don't have one follow-up.
Yep.
I didn't realize so Casper is a DAG protocol?
Naive Casper, what we call basic CBC Casper, is a blockchain protocol. It's a chain protocol. Our implementation, we have some unique properties in our global state architecture that enables us to do a multi-parent implementation. So we can actually do a proper DAG implementation with very, very low orphan rates.
So that's not what they're proposed. It's kind of what they're doing still a chain.
They are still doing a chain. That's right. Yeah. Yes.
How does this compare to, say, you made reference to, what's the name of the, Hashgraph. What I'm thinking.
Yep. Hashgraph, it's pretty simple. They are using a fork choice rule, I think, with PBFT, and they have leader selection as well. I believe Hashgraph also has a DAG. The thing is that they're not permissionless, right? Hashgraphs, you have to become part of the validator set. So they don't have a fault-tolerant protocol. So I'm pretty sure they don't have slashing because the validator set's trusted, right? And so they just assume that all the validators are honest. And this, I don't know how similar their consensus protocol is to ours, but from what I understand, it's a fork choice rule with a PBFT and leader selection. I don't think they even have leaders. I think it's just fork choice rule with PBFT. Yes?
What is the timeline for the mainnet launch? Obviously, you guys have been working on this for a long time.
I have, yeah.
Work into this.
We've put a lot of work into this. So I worked with Vlad on a project prior to Casper Labs, myself and our lead developer, Michael Birch. We've been working on the CBC Casper protocol for over 2 years now with Vlad. We learned a lot on the last project that we worked on this implementation. We've learned even more on this particular project. We anticipate our highway protocol implementation to be ready sometime by the middle of the year. That would be the testnet timeframe. Optimistic, end of Q1. Realistic, probably Q2. The protocol is getting the protocol right and secure has been very challenging because there's a lot of economics that are involved. So you can imagine we have to figure out, what are the min-max bonding thresholds, the overhead associated with the validator set size, what are the slashing amounts that will keep the security of the network high? Do we want the slashing to start very low in the event that there's bugs and have it progressively go up as adoption of the blockchain increases over time, right? Because you want to have a very secure blockchain eventually, but right now you have to acknowledge that there may be defects in the system that would cause validators to lose their stake. So there's a lot of economics work to do, right? We've got 2 full-time economists on the team, and this is all they're focusing on is like this notion of this Nash equilibrium you want to get to on the economic side, right? Incentives and disincentives to encourage validators to do the right thing. So the protocol from a computation perspective doesn't have to do as much to keep everybody honest, right? The honesty comes from the economics, not from the protocol. Yeah.
Summertime next year.
Summertime next year. We do have, like I said, this is a live network that my node is connected to here. Our DevNet. I can show you that quickly here. Here it is. So this is our developer network here. This is the latest block DAG, but you can see this is from our node testing session this morning. We tested with the DevNet. We've got about 700, 800 blocks in here. And then we also have our GraphQL interface, which is kind of cool. This enables you to query the developer network, so you can get the latest information on the latest block, and then you can use that. This is somebody deployed a small contract here, so this is the latest block. I can go ahead and query that, and you'll see here this int value changed to 2. That's because he ran his little contract and incremented his little counter there by 2 from 0 to 2. And so this is basically the application insights that we provide to DApp developers to let them debug and troubleshoot their on-chain contracts, just by way of example. Yes?
How do you, say this gets huge, being everyone's using it, lots of smart contracts, you have the fees moment. What's the goal to avoid the inferior problem?
Remind me what the inferior problem is. Sorry.
Everyone accesses one very massive, huge, centralized API to access the blockchain for lifetime apps, because
Yep.
those have UA cost of running nodes, and
Yep.
validators maybe don't provide.
Yep. So there's a lot of it's a sharding. I mean, it's a sharding question, right?
Validator required to provide to a lifetime.
Right.
And if it's not everything that a lifetime might need, then you end up having to access supernode APIs either at the cost or at goodwill
Right.
for services.
Yeah, so the question is, you've got this massive central computer, and how do you get around from everybody accessing this single massive central computer? The idea, what you're talking about now, is sharding the global state, right? And so what you're basically talking about is that not all the validators process all transactions. Each of the validators, or some subset of the validators, process some subset of contracts, and they have a partial state.
That's actually not what I'm referring to.
Okay.
I'm referring less to the work that each of the nodes have to do in sharding of that. I'm more referring to what do light client apps, dApps, wallets, what interface do they have to be able to query the network for all the information that they can possibly need. And so in the Ethereum world right now, it's either you go run this massive full node, which is heavyweight and very expensive,
Right.
or you query a centralized service like Infura.
Got it.
And that ends up becoming the only choice.
Mhm.
There are a few others that are not Infura, but basically the choices are becoming very, very centralized, where no one's really running a full node, and it's simply opting to go with a commercial API.
Mhm.
What is effectively being provided by these validators that could prevent that, where I can just access a validator willy-nilly as a light client participant of the network? Is something we thought of in that regard, having looked at many different blockchains and the different solutions to that, like in Bitcoin, well, it's cheaper on a node, but the average person still doesn't want to.
Right.
It's cheap enough where there's a ton of nodes running supernode implementations like Electrum. The world of Ethereum is the polar opposite. And then
Right.
somewhere in between, which is an interesting model, is EOS, where each of be a validator like a block producer, people vote on not just whether or not they are publishing correct blocks, but they get voted on by just doing good things for the ecosystem.
Mm-hmm.
Right? So a block producer gets more money if they just do stuff that the ecosystem likes. One
Right.
of those things is
Right.
to provide standardized APIs for light client apps to access. And this is a big question I've had for how certain blockchains can scale to really addressing the global audience.
Yep.
So what's the intended
So the GraphQL interface, you're actually pinging the developer network, the DevNet right now. There's 5 nodes in here. There's a load balancer in front. This service is provided by the node software. So this is baked into every validator node. So this is not a separate service. This runs on every single node on port 40403. Now, arguably, validators may choose to not expose their GraphQL port, but the idea is that every node will offer a GraphQL interface. I believe some validators, if they want more business, will offer this service to their customers if they want to process transactions, right, for their customers.
Is that interface required in order for them to validate transactions?
It's not required in order for them to validate transactions. So there is that caveat that they could potentially decide. Yeah. Yeah, yeah. So they could potentially choose to not do that. Now for light clients could arguably run a read-only node. You can run a read-only node. You don't have to stake the network, right? You probably don't even need to keep the full blockchain semantics and have a massive amount of compute or participate in consensus. All you want to do is get the blocks of the network, and then you can run a GraphQL interface, right? Because you're not participating in consensus, you don't need to really even worry about consensus values, right? But you could arguably run a node. It doesn't need to be a massive node, but you could run a node and get your own GraphQL interface if you wish, or you can choose to use it from a validator. I completely see your point. I don't know any other better way, because the reality is you're using shared infrastructure, right? It's like AWS. If you're using AWS and you're asking AWS for bandwidth and compute, they're going to charge you for it, right? So it's reasonable that the validators will charge for those GraphQL services in time. The best thing that we could do from an engineering perspective is make it easily available, baked into the architecture, and very obvious in terms of what it does, right? We feel that even getting state queries from Ethereum is very, very difficult, and we wanted to make that an order of magnitude simpler. And so we felt like this GraphQL would simply do that.
So in respect to Ethereum, I mean, coming from not like a DApp developer, more like a wallet role, the base Ethereum node gives you balances of Ethereum fairly easily. And actually that's kind of it. And anything after that, you kind of need a full node to index data off the blockchain. What does a base node have, unless they turn it off in the GraphQL interface, what does it give you as far as being able to know transactions that have happened on an address and balances of address? Potentially, I assume, this architecture being very flexible would support tokens in some.
Oh yeah, 100%. It supports tokens completely. Yes, Turing complete.
Query that information from a basic stock node.
Yep.
Is that expected to all be available? Or
Yeah, that will all be available. And we're actually augmenting the GraphQL schema and interface to offer more information, like show me the last set of deploys that have happened, show me all the deploys for this account, show me all the salient transactions that have happened for my particular application. Send me a stream of finalized blocks. So just, you can create a subscription service where it just sends you the finalized blocks as blocks become finalized by the network, instead of having to constantly query for it. But yes, that will all be baked into the GraphQL interface and in the node. We already have balance and we already have the balance query built into the gRPC interface right now. So if you just run Casper Labs client balance, you'll get the balance. But you can also do a lot of these more complicated queries with GraphQL directly from the gRPC endpoint as well.
it is an account-based system, I presume?
Yeah. Yeah. It is an account-based system. Yep. Other questions? Yes,
What are
Nelly?
some of the use cases that you think people are talking about for the support protocol?
Yeah, so the use cases that get really interesting are the ones where you really want to see a decentralized, high security blockchain, right? We think that's one of our key value propositions, is that we are fully decentralized. So when you talk about things like decentralized and public data, right? So we don't necessarily have a privacy concern unless they want to encrypt the data and then put it on the blockchain. So some of the interesting things are proof that this event happened on this day, right? Something very basic, like if I want to do supply chain, but a lot of supply chains are private right now, but if they can hash the events and put them on a public chain, that if there is a supply chain failure, that vendor can then show that, well, we had this failure, but look, we've addressed it now. And we can choose to be transparent about our supply chain after the fact, right? They definitely have privacy requirements where they can't be transparent before the fact because of security requirements, but after the fact, once everything's been said or done, if they want to be transparent that, yep, we're not using that provider anymore because there was an issue in our supply chain, we can demonstrate clearly that we're using this one, and it's completely trusted, right? When you're trying to restore consumer confidence, it gets really important. Obviously, any decentralized finance applications will be very interesting if the chain is high security, right? So if you want to tokenize assets or do anything with kind of a token economy type decentralized finance. The other use cases that we've been talking to folks about are in government, right? So public data, you think about things like title theft. You could potentially put title on the blockchain, and it gets to be a very interesting thing where you don't have to worry about somebody coming in and taking your title. that follows the unforgeable reference weighted signature model very closely. It's an interesting use case. Those are just some of the ones. We are talking to a lot of companies right now and are looking for like really what is that, I don't want to say the killer app or the unicorn, but really that killer insight about what it is we've built.
How do you decentralize the punishment side of this if you don't do what you're supposed to, or you messed up?
The slashing? Mm-hmm.
Yeah.
Well, it's who slashes you?
Yeah.
So what happens is the protocol will detect the equivocation, and then all the validators, so when you get slashed, that block gets out into the network and the other validators sign it. Right? So it gets processed like a transaction. But it's just a transaction where your stake is slashed.
Right. And where did your stake go after it's been slashed?
Great question. The stake basically gets burned. The idea is that it gets burned, right? We don't want to give anybody an incentive to slash stake. So when stake gets slashed, everybody loses. Like nobody profits from a slash. Right? Because the minute you start saying, oh, we'll slash the tokens and put it in this account, then now you've got an incentive, or if for them to slash somebody, or if you say the slash tokens get distributed to the validator set, now you have an incentive for griefing, right? So slash tokens are burned. They just go to oblivion. Again, more of the economic considerations we have to, yes?
Have you thought of just simply bootstrapping via proof of work?
Bootstrapping what?
From using proof of work and then migrating off of it, which is effectively what Ethereum did, but they just happen to have a very, very long bootstrap.
When you go from proof of work to proof of stake, you wind up having a big incentive problem because the equipment required for proof of work is fairly specific, and those are physical rigs and operational expenditure, CapEx, and OpEx that the validators need to incur. And so, you're best off just starting straight up with proof of stake because your incentives are aligned from the get-go for your validator set. The incentive mechanisms for proof of work and proof of stake are very different.
Correct.
Transitioning incentives for validators is tough, I think. It's actually a very powerful, it has very powerful inertia, right? It's very hard to change and move economic incentives.
As long as it's baked into the consensus rules, right, as soon as you start, then you kind of don't need to change it. Like everyone knows, like you're going to mine up to block 100,000, and it's baked into the rule set. And at that point, you transition to stake, whether gradually or immediately. And so you're not really changing their mindset. They're already hopping on board knowing that we're going to buy mining equipment that's going to be out of date in 100,000 blocks. So it's not like Ethereum where we're having to actually change these mindsets because people are not prepared for this.
Uh-huh.
You make it kind of from the get-go and then not have to deal with this problem of how to do bootstrapping.
Well, the problem for bootstrapping is actually a solved problem.
Solved with like a regulatory burden, with a lot of very regulatory burden, and not many people can actually join initially.
Yep.
So you don't have actually a fair start, right? Because people are unaccredited investors in the U.S. cannot have that in their own circle. So
That's right.
That's very different from proof of work. So by starting with a proof of work for some period of time, that you can even make where during that period of time there's been transactions getting done. Like there's a mine in your mine, and only when you hit a certain block height then you actually are using the network to do transactions.
Yeah, but unless your hash rate is really, really high at the onset, your network still won't have any value in your token, right? Because your stake comes from the value of the initial value of the network and token. So you still won't have more security than you would if you did the private validator sale to bootstrap the network.
Which is actually even not necessary because you don't have any transactions on the network.
That's true. That's very true. Yeah.
It's a way of selling it. You're just selling for electricity.
No, it's very true. I mean, so for us, because there isn't a lot of transactions in the network, one of the ways we're handling it is that the slashing percentages will be very low, right? Now, from the moment the network goes live and the moment the first token offering is available, anybody can acquire a token and join the network. Arguably, there will be no limits on our end, just the initial validator set.
Right, exactly. Bootstrapping. That's what I'm
Yeah,
referring to, bootstrapping.
but from the moment the tokens go live, it's completely open in our network.
So you know, like in Bitcoin, once you mine a block, you can't use it for 100 blocks. That 50 or 100 blocks. And so the rough equivalent could be used to bootstrap, where for when you mine a block and it completely unusable coins for 100,000 blocks. And so the security of the network is irrelevant until you hit that mark, and then you transition.
Mm-hmm.
That gives you the true fair start, and it still allows you to make it where the network benefits from all of proof of stake in a transactional world, where
Right.
you are sending and receiving, you got a DAG and whatnot. I feel like that's something that, I don't know, the new projects leverage that as a concept, and it seems like it's
No projects have leveraged that. So my intuition tells me there may be a reason which I would actually like to talk to Vlad about that and ask him what his thoughts are. I'm sure he has strong opinions about it.
the only opinion I hate to say it is there's no money to be made. I'm just saying.
Yeah, I mean, the desire. Yeah, I mean, so I agree with you that there is definitely a financial incentive in that, but the goal is to have the network be completely open and as accessible to individuals as possible, right? Now, one of the things we have to be real about, at least with the CBC Casper protocol that we're building, is that there is this notion of network overhead, right? And so we can't have 10,000 validators on the network and expect that the message overhead isn't going to get untenable in the beginning, right? So the desire is to have it be permissionless so that we can have validator set rotation. The desire is to have as much open access as possible, but we need to keep the protocol moving forward for the time being, and then once we have sharding implemented, over time we can increase the level of access, right? That's the current thinking and the realities of what we're up against when it comes to like current network throughput, current bandwidth, right? I expect that will go up over the next 5 to 7 years, and blockchain will become even more accessible over time, right? We've already seen the orphan rate drop on Bitcoin over the past 3 to 5 years, and I expect that throughputs on blockchain networks will go up and accessibility will increase as well. But yeah, I mean, I don't disagree with what you're saying, but I don't know that the incentives to just, well, I'm going to get rid of my mining rig now and just go to a regular x86 machine because that's the way you guys wanted to bootstrap. for a lot of the banks to have their own cryptocurrency, but I also think that they have a real privacy concern, right, for competitive reasons. They don't want their competitors to see any information on their blockchains, which is completely reasonable. You know, private, as much as the government would hate private transactions, I think private transactions in the blockchain are probably going to be essential. I think it's only a matter of time. I also think decentralized blockchains are hugely, hugely important, because can you just imagine if a central authority can shut off the money? Like, you can't even go to like a dollar bill. That would really suck. So I think decentralized blockchains are hugely important for all of us. The dystopian portion nightmares that I have about blockchain. Yeah.
When you were saying behind the curve in the US, you said from more consumers? Or I didn't know.
Regulatory, like regulatory perspective. Yeah, our adoption of it and just how we're thinking about it as a country. Like China just a couple weeks ago came out and said, right, the president came out and made a very bold statement about Bitcoin and about cryptocurrency and how China's going to have like a full-blown initiative around cryptocurrency. That's huge, right? Like they're way ahead of us.
They also retracted that statement. I think he came out and said, don't get the wrong impression here. We're not down with cryptocurrency, but they are down with creating their own currency.
Sure.
So,
It's all about control,
yeah.
which is why decentralized chains, I think, are hugely important. I mean, I see it as a huge, you know, leveler, a great leveler, and putting more power in the hands of the individual, as well as, you know, preventing things like the Fed, you know, diluting our money. It's another topic. That's another meetup.
You're right.
Yeah.
Well, I really appreciate everybody coming out today and you coming to speak and
Thank
fielding
you.
all these questions.
Yeah. Thanks for listening to me ramble. I appreciate it, guys.
I found it very useful and insightful. So thank you. I appreciate it.
Thank you.
So if anybody has any announcements that they want to make, now is the time. So if you got anything that you want to talk about or share, come on up and make your announcement. Can we get that microphone for me?
Yeah, totally. There's that, and there's that.
And no announcements today? All right. That's easy. I did mention, like I said, the holiday party, hopefully December 19th. And look out for a lot more events, I think, in the future. At least two type of like speaking type events, and then one general casual meetup a month. So 2020, we're going to be cranking out a lot more stuff. So hope you guys can make it, and we'll see you all soon.